So now that we understand the basic physics of sound waves and how that applies to medical ultrasound, let's more deeply understand the interactions of those ultrasound waves in human tissue. And to start off, let's review how the sound waves are produced in more detail. I said that the transducer changes electrical energy into sound waves. Well, within the transducer, there is a layer of crystalline material. And when an electrical current is applied to these crystals, they change shape. This is something called the piezoelectric effect. And when those crystals change shape, they generate a vibrating-like motion, similar to a speaker pumping back and forth, and that's what generates the sound waves. And as we talked about before, the sound wave then hits the tissue in your patient and it's transmitted back to the transducer. When the returning echoes hit the crystalline material, it causes them to change shape again, which then generates an electrical current, which is transmitted back through the ultrasound transducer to the machine to be processed to form the visual image, as we discussed previously. So after the ultrasound wave is produced, how is it transmitted through the human body? Well, the speed of sound in any tissue is predominantly determined by the characteristics of that tissue, such as its stiffness or its density. If you remember from high school physics, the more dense a material, the faster sound is able to travel through that tissue. And the converse, the less dense the tissue, the slower sound travels through it. And if you look at the human body, there's a pretty wide range of tissue densities in different tissues. On one extreme, you have the lung. And the speed of sound in the lung is approximately 600 meters per second, because the lung is predominantly filled with air. On the other extreme, you have bone, which is dense, and the speed of sound through bone is 4,080 meters per second, much faster. And then you look at fat, travels 1,510 meters per second, liver 1,555 meters per second, blood 1,560, kidney 1,565, muscle 1,600, etc. And thankfully, all of the other soft tissues in the body can be averaged at around 1,540 meters per second. So if you exclude lung and you exclude bone and you just focus on the soft tissue, then the average speed of sound in the human body is 1,540 meters per second. This is what the machine uses to calculate the speed of sound in soft tissue. Well, if you do the calculations, this comes out to a 13 microsecond per centimeter round trip travel time. What does that mean? Well, if a sound wave is produced from the ultrasound machine, it hits the patient, it returns, and all of that happens in 13 microseconds, it means that those sound waves returned from 1 centimeter of depth in the patient. If 26 microseconds, 2 centimeters, so on and so forth. So now we're going to touch on, in a little bit more detail, the concept of resolution. And there's actually 3 different types of resolution: spatial, temporal, and contrast resolution. And predominantly we're going to focus on spatial resolution, which is the ability to resolve 2 different points in space. And if you remember previously, we said if you increase your frequency, you increase your resolution. And this is because the higher the frequency, the smaller the wavelength. And if you have a very small wavelength, you can pick out 2 different distinct points in space, resolve them that they are 2 different points. However, if you had a larger wave that has better penetration, but remember poor resolution, it's not able to resolve those 2 points as 2 separate points, and it will display them as one. on the ultrasound machine. Well, besides frequency, is there anything else that we can do to improve our resolution? If we look at our ultrasound transducer and how it transmits the ultrasound beam is actually transmitted in this fashion. There's this concept of convergence and divergence, and then a focal zone. So the ultrasound beam converges to the focal zone, and then it diverges away from the focal zone. And the beam is most narrow at the focal zone. So at the focal zone, you can much more easily pick out two different distinct points, where those same 2 points, here and here, would appear as one, or here and here would appear as one. But at the focal zone, because the beam's narrow, it is able to resolve those 2 points and your image is more clear. Later in the course, we will describe how to use the focal zone and focal point to improve your resolution, but just understanding the concept at this point is the most important. The next concept we'll discuss is acoustic impedance. An impedance is simply a measure of resistance of the travel of sound through tissue. And each tissue has its own inherent impedance characteristics. Let's call this tissue 1 on the left, and let's say it's kidney, for example. And on the right, let's call this tissue 2, and let's say it's liver. Now, tissue 1 on the left is going to have one impedance, and tissue 2 on the right is going to have one impedance. The greater the difference between the impedances of each tissue, the more the sound is going to reflect back to the ultrasound probe. The more similar the acoustic impedances between the tissue, the less the sound is going to be transmitted back. For example, the incident beam comes and it hits the interface between the kidney and the liver. If there's a large impedance difference, a large portion of that sound is transmitted back, and a small portion is transmitted through. If there is very similar impedances, then the incident beam comes, hits the difference of impedance between those two tissues, and a large component is transmitted through, and a small component is transmitted back. Another thing that contributes to how the sound is reflected back to the transducer is what type of reflector that the ultrasound beam is hitting. And we primarily group these into two different types of reflector. One is called a spectral reflector, and this is a very smooth reflector like the diaphragm, for example. And the other one would be a diffuse reflector. And this would be something like cirrhotic liver, for example. Now on a spectral reflector, the ultrasound beam comes and hits that spectral reflector and then is reflected back in a very smooth, intense fashion to the ultrasound transducer. So on the screen it will appear smooth, homogeneous, and bright because most of the sound waves that were transmitted to the tissue were reflected back to the transducer. In contrast, a diffuse reflector, the incident beam hits it, and then a lot of those ultrasound waves scatter in different directions, and only a portion of them reach the transducer. So it gives it more of a speckly type of appearance because of the scattering of those ultrasound waves, and also the intensity or the brightness of the image is lower because there's less amplitude of waves that return. So now we come to our beloved concept of refraction. And if you remember from high school physics, there's that classic example where you stick a pencil in a glass that's half filled with water, and it appears that the pencil bends when it's stuck in the water. And refraction has to do with the bending of waves when they travel through two different mediums that have two different speeds. So in our case, let's look at the left example. We have an ultrasound beam, the incident beam, coming through a tissue in which it travels slow, meeting a tissue in which it travels fast. And due to the abrupt change in the speed of sound between those two tissues, the ultrasound beam bends and travels away from its original path, thus creating a larger angle here. Now conversely, if the incident beam is traveling through a tissue in which it travels fastly, and the abrupt change to a tissue in which it travels slowly through, then it moves toward the original path, thus creating a smaller angle. Why is this important to ultrasound? Well, we'll discuss it mainly when we're talking about artifacts, but just understanding the principle is the important part at this point. Well, the last concept that we're going to talk about today is attenuation. And this is a pretty simple concept. It's just a decrease in the amplitude and intensity of the ultrasound beam as a function of distance. And this is pretty simple to understand. If you're standing close to a person and they're yelling, it sounds louder than if you're standing far away. Because with distance, the intensity or the loudness of the sound dissipates. So we can depict this on a graph with intensity on the y-axis and distance on the x-axis. And the closer you are, the more intense the sound is. But as you go further away, the sound becomes less intense, to where eventually you can no longer hear it at all. Well, the importance to ultrasound is that attenuation is highly dependent upon frequency. So as we increase the frequency, we increase attenuation. And therefore, high frequencies, as we've learned previously, cannot penetrate or travel as far because they attenuate more quickly. Okay, well, we looked at various interactions of ultrasound in soft tissue. Next, we will learn about ultrasound transducers.